Hello physics students. So in the last video we used Ampere's law to figure out the magnetic field for cylindrical symmetry current that was going through like a cylinder. Today we're going to be applying Ampere's law to planar symmetry, and we're going to be doing two examples today. One for a sheet of current and one for a slab of current. The infinite sheet of current is very thin. In other words, we assume that it has almost no thickness to it, and we have current that's coming out of the board in this case, but it could also be going into the board. And again, it has to be infinite for our analysis to work. In other words, the dimensions this way have to be quite large compared to how high we are above the plane. Again, infinity is always a relative term in physics, so it just has to be much wider than we're studying, than the area we're studying. So we need a new symbol for the current density because the other symbol we use, capital J, that was for current spread over an area. Now we need a symbol for current spread over just a line. So the new symbol I'm going to use is the Greek letter alpha from the Greek alphabet, and it's going to be defined as current, the current in a certain length of this sheet divided by that length, and so it'll be amps per meter, like a concentration of how packed the current is per meter. All right, so in order to use Ampere's law, you still first need to understand the Biot-Savart law so you can sort of figure out the directions of the magnetic field and the symmetries involved, so you can think of an appropriate Amperian loop. So in this case, I already drew the Amperian loop, but before you would draw this, you would have to think, okay, let's take a point up here. Which way does the magnetic field go? Well, there will be a little bit of current right here that produces, according to the Biot-Savart law, a bit of magnetic field dB like this. And then over here, symmetrically to this point below here on this side, the same distance, there's a bit of current that by the right-hand rule and the Biot-Savart law would make a magnetic field perpendicular, right-hand rule like this, like that, another dB. So these two would have the same up and down component, canceling. The only part that survives is a horizontal component. No matter how far I move this way, there will be another point over here canceling that upper component of this part over here with a downward component. So from that consideration, we know the magnetic field above this sheet will be perfectly horizontal. And if you do a similar analysis below this sheet, right-hand rule, you will find that the magnetic field caused by this infinite sheet goes perfectly to the right horizontally. So again, you have to know this because now we can pick an Amperian loop that will conveniently determine the magnetic field around this plane. And the loop that we're going to pick is a rectangle like this. And so we apply Ampere's law to this Amperian loop, B dot ds equals mu 0 I enclosed. And the reason why we pick a rectangle is because the dot product for the magnetic field dot ds, when we integrate around, well, maybe I'll just leave the vector symbol off. That looks a little confusing. The B ds, that dot product is 0 along this side and 0 along this side because of the 90 degrees between the B and the ds. So the only part of the integral, when we integrate all the way around this Amperian loop that is not 0, is along the top and bottom because the magnetic field is in the same direction as our ds as we integrate. So the bds is not 0 up here. And then when we come around, the ds is now going this way, aligned with that magnetic field. So that's the part where the line integral bds is not 0. And because this is a constant magnetic field, because this is an infinite plane, or thought of as infinite, then we could just simplify this to b times the length across the top plus b times the length across the bottom. So integral bw for the top and bottom. The current enclosed, I've shaded in red here so for your convenience so you could see it better. What it's going to be is the amps in here has to be the amps per meter times the meters will be amps per meter times meters gives me the amps trapped in coming out of our Amperian surface, which is what I enclosed is. So there's the setup of Ampere's law. By the way, I failed to mention this in the last video, and I'll mention it hopefully at the end of this video, that the second line of the Ampere's law derivation, like the second line of Gauss's law, is really where all the thinking is. The rest, simplifying, is just a little bit of algebra. So I'm going to remind you again to go back to the last video and look at all the second lines, those big giant lines when we had the coaxial cable, and really understand that second line where all the terms come from, and the rest, the answer will follow. And by the way, most of the credit on the AP anyways is that second line usually. And so even if you make an algebra mistake simplifying, you get most credit when you set up that second line like this right here. All right, so let me create a pause before I go on, so give you a chance to catch up if you need to, copying this down. All right, so moving on, we just combine these because the B at the top and bottom from symmetry thinking, they're the same magnetic field because we're the same distance above and below. And so we get 2BW equals this side over here, and then you just simplify, divide, and you get your answer. So before I explain this is a constant, what I want to do is first do a unit check. Remember, we always compare to mu0 I over 2 pi r, so we need a mu0 amps per meter for units. And so we have our constant of mu0 here, our units, and then alpha is amps per meter. So we have mu0 amps per meter, we have the correct units. So our formula has at least the right form. It is a constant. Notice there's no z coordinate here. So it didn't even matter if we didn't straddle this plane the same distance. We could have had this Amperian loop be more above than below, but because the magnetic field did come out as a constant. So the infinite sheet, constant magnetic field, no matter how high you rise up that plane. Okay, so the next example is the infinite slab. So instead of a very thin sheet of current, now imagine we have like a parking lot with asphalt, and the asphalt conducts electricity, right? So big, giant parking lot, maybe at the shopping mall. It goes, you know, almost a half mile in either direction or something. And we have current passing through that slab, and this time the current will have the old symbol for current density because the current is spread over 2 dimensions. So it will be amps per meter squared, like a concentration in a certain area. The slab is a thickness d apart. And so if we label the center of the slab at z equals 0, then this is positive d over 2, and this is z negative d over 2. And once again, we need to know before we even draw our Amperian loop, I'd put it here already, but you need to be able to reason out from your Biot-Savart law kind of thinking and analysis, not the magnetic field, what it is in terms of magnitude, but what the patterns are and the direction of the magnetic field, so we can then even select the correct Amperian loop that, or one that will give us useful information about the magnetic field. So how do we do this reasoning? Well, first thing, we can reason out that the magnetic field at the center would be 0. See, I already put these here, but let's reason it out over here, how I got these arrows. So let's suppose I imagine a little bit of current over here. What magnetic field does that produce over here? Well, if I use the right-hand rule and I draw a little radius vector, then the magnetic field caused by this piece of current will be going up in this direction. I can pick another piece down here that will create a magnetic field by the right-hand rule going that way. And then maybe another piece of current right here that creates a magnetic field going this way. And then another piece over here that creates a magnetic field going that way. So those 4 arrows, if I am symmetric left and right and up and down the same amount, those arrows will cancel. So no matter what point I pick here, I could pick 3 other ones to make that will cancel the magnetic field here. If I pick a point over here, then I could pick points here, here, and here, and those all cancel there. And so the magnetic field will always cancel right at the center of the slab. But if you go off center, like maybe a point up here, now what you can reason out is that all the points from this portion of the slab, by that symmetry argument, cancel and produce no net magnetic field. But look at all these other points down here that now have an overall magnetic field that will, current coming out of the board, that will produce a magnetic field to the left. And like from over here, here and here, produce a magnetic field horizontal. And the more I get closer to the top of the slab, the more current I'll have below me that has no current above to cancel it. And so the magnetic field will gradually go from 0 to increasing to a maximum value at the surface of the slab. And above, the magnetic field goes also to the right because of, again, I could have 2 points here canceling their vertical component, producing a net magnetic field to the left. So that's how I know the pattern is to the right here based on the current coming out of the board. Increasing magnetic field, and maybe a constant we'll find out to the right up here, and then down here from the right-hand rule going the other way of the same pattern. Now, all that thinking, again, is necessary so that you know the pattern so you can pick the right shape Ampere loop. So I'm going to pick a rectangle again, and I'll explain how that will then impact the integral as I go along to the next example, to the calculations. But first, let me create a pause to allow you to catch up copying these notes down if you need it. Okay, so now what we're going to do is first start for finding the magnetic field inside the slab. In other words, for z less than d over 2. I pick my Amperian loop here, and so I write out Ampere's law. The main thinking is right here in the second step, because now I know that, like over here, the magnetic field along these sides here will be perpendicular to my ds as I'm integrating around this Amperian loop. Then ds goes this way, b goes this way. Over here, ds goes this way, b goes that way. So this dot product is b ds cos theta 0 along these edges. But along the top and bottom, the magnetic field will run along the integration. b ds will not be 0 because they are aligned on the top and on the bottom. So that's why with the constant b, we could just say bw plus bw along the bottom. That's this integral along this Amperian loop, only non-zero top and bottom. The I enclosed, well, I shaded this in orange, and now we'll use J times area is I enclosed. Amps per meter squared times meters squared gives me the amps inside there. So here is the current density. What is the area of this shape? Well, first of all, it's W wide. I didn't put that on the diagram. I should have, but maybe I'll do it inside here. W wide, okay? So it's W wide. And how tall is it? Well, we've got Z here, but Z here also, because from the middle out to the top is Z. So the whole height of it is not Z, but 2Z. Okay, so this is width times height, 2Z. So the area is right here, this term times current density. And then that's the thinking. The rest, again, is just simplifying, combining these because these are the same, and then we get our answer here. Notice the magnetic field follows that pattern we already deduced from our Biot-Savart law, kind of thinking just conceptually, that at Z equals 0, the magnetic field is 0, and then it gets bigger and bigger the further you go out from towards the edge of the slab, okay? Unit check. So again, we compare it to mu 0 I over 2 pi r, which is units of meters. So we have our mu 0, J is amps per meter squared, and then Z is in meters, and you see we ultimately simplify to the correct units, so the formula has at least the correct form. All right, so let me create a pause to allow you to catch up if you need to. All right, so now what we have to do is move on to outside the slab. So make a little room. All right, so Z greater than D over 2 is a way to say outside the slab. So what I'm going to do now is pick a new Amperian loop. And it has to, if I want the magnetic field out here, it's got to extend to this region. Again, it'll be a rectangle. And I'm going to pick a rectangle like this. Okay. Well, not, it kind of goes a little wavy there, but it's supposed to be a nice rectangle. And so I'll apply Ampere's law to this rectangle. Now, why did I pick such a rectangle? The same reasoning here. I know that the BDS will be 0 along the sides, and the only part of the integral that will not be 0 is along the top and the bottom, where B and ds, the direction of integration, are aligned along the top, and BDS are aligned along the bottom. So that will give me, again, B top times the width W plus B bottom times the width W, that's along the bottom, will equal mu 0 I enclosed. And this time the I enclosed, well, maybe I won't color the, you know what, red won't show up that well. I mean orange against red, so let's do green. All right. So that's the I enclosed. So I need to use J times area for that. The amps per meter squared, J, times the meter squared, which will be the area of this green shaded region, which will be the width of our Amperian loop times the height here, which is just the thickness of the slab. Again, this is the main thinking. BDS along the sides here, BDS 90 degrees, so zero integral, just along the top and bottom. That's on the left side, and then the I enclosed. Now we just need to do a little simplifying. So these are the same. And so I just need to divide away the W and then divide away the 2. And there is the magnetic field above and below the slab. So first point, it's a constant again. There's no Z coordinate here. D, the thickness of the slab, is a constant. So as long as you don't go like a mile above this parking lot, but maybe 1 meter, 2 meters, you know, in that region where the parking lot still looks infinite horizontally in all directions, then the magnetic field will be constant with altitude. And then the other thing we have to do is I recommend a unit check. So again, we need to have magnetic field in terms of mu0 amps over meters, the units of mu0 I over 2 pi r. So we have our mu0, we have amps per meter squared again, times distance, thickness of the slab in meters. We see that the units, this formula appears to have the correct form. All right, so let me create a pause to allow you to copy this down. All right, last thing is the graph. Very often, as you know, you're asked to create a graph of the magnetic field in all the regions. So here's the magnetic field axis B. Here's, you know, it's a little confusing. Z-axis is going to be going now sideways. Usually we call that x, but that's the height above the plane. And so what we saw from this formula is the magnetic field increases linearly, reaches the maximum value of this outside the plane, and then it's a constant. So that occurs at z coordinate of d over 2. And then this value is this, which I'll just write as one fraction maybe, mu0 j d over 2. Below the z equals 0 point, when we go into negative z coordinates, the magnetic field suddenly switches from one direction to the other. So maybe we'll make it negative like this. And then at negative d over 2, we're outside the slab again, and then it's a constant. And the constant value will be the same value, but in the opposite direction. So what I will do is I'll label this negative mu0 j d over 2. Okay? All right, so let me create a pause to allow you to copy this graph down. All right, one last point I want to make is you could have chosen, and you don't have to do this because you know, it'll just mess up your notes. But instead, an alternative kind of Amperian loop is this. Okay? And for this one, you could have had this as an Amperian loop. Okay? Why are these viable options? By the way, these are the only two viable options. This was symmetric about z equals 0. You cannot have an Amperian loop, for example, that goes like this, where it's non-symmetric. Why is it okay this non-symmetric, but that non-symmetric is not okay? because this would produce two unknowns, different magnetic fields here and here. And so we would have B top and B bottom. We would not have been able to combine this like this. And so we would have two unknowns. We would not be able to solve for the magnetic field with this Amperian loop. With this Amperian loop going through Z equals 0, we know the magnetic field here is 0. So this is okay, because what would happen in our analysis is that this term would be gone for this Amperian loop. And the I enclosed would not have this 2 over here. And so we would ultimately be missing it, but we get the same answer. So that would work. And the same thing over here. If we had this as our Amperian loop, it would make this term not here because there's no magnetic field, so that part of the integral would not be there. But now the I enclosed would be, because this area now is d over 2 times w, so that we'd have to put this here. And ultimately we'd get to the same answer. So two different possibilities are both fine. So that's Ampere's law for planar symmetry. Again, I want to remind you, look at these second lines, study them, okay, because that's where the thinking is. This is just, memorizing and rewriting, but this is the thinking. Master that. Go back to video Ampere's law 1 for cylinders. Look at those second lines for the example 2 and 3. Study them for the, one is the easy, the line of current, but the other one, the coaxial cylinders, for all three regions, study the second line that I wrote on the board and really know where all those terms are, and then you'll do great on the test when it comes around when we get to the test. All right, so look back at those notes, and I hope you enjoyed today. I hope you learned a lot, and I will see you in the next physics video.